Thank you. Good afternoon. Hopefully you're not all having food coma from the chocolate cake at afternoon tea. So my name's Cath. I'm from Curtin University, and I'm going to give you an overview of the MWA Epoch of Reionisation project. So the MWA, for those who don't know, is the Murchison Wide Field Array. It is a low frequency radio telescope built in the Murchison region of Western Australia. As Elaine introduced this morning, we have a new Wodjiri name for the observatory site. So I'd like to acknowledge the Wodjiri Energy as the traditional owners and custodians of the land on which we're building the square kilometre array telescope, but also where the MWA exists. And that's in Yarimana, Ilgari, Bundara, CSIRO's Murchison Radio Astronomy Observatory. I really like this photo. I took this from Jack Line. I'd like to thank Jack for providing some of the slides for this talk. This is one of the central regions of the MWA. You can see it's made of these tiles, as we call them, of 16 dipoles. For reference, they're about 5. They look like little spiders on the ground, and a lot of the time the site does look like this. The grass grows up after the rains. It grows up between the tile, but because we're using radio observations, we don't care too much about what's happening with the grass, although the water content of the soil does actually affect our observations. But this is the telescope that we're using. So these are the MWA members as they were about a year ago, and we have over 100 collaboration papers now within ASTRO 3D. These members sit mostly across the Curtin University and Melbourne nodes, but these ones that I've highlighted here in the ASTRO 3D pink are the people who've moved on in the last 12 months. So these are PhD students who've gone on to jobs or postdocs who've gone on to work in the public service or into faculty positions overseas. And with, as with a lot of the projects within ASTRO 3D, over the next 12 months, we're going to be losing more of our capacity. And so we're sort of a race against time to try and finish off some of the great projects that I'm going to talk to you about. And I co-lead this project with Rachel Webster from the University of Melbourne. So these are some slides that I've shown previously, but just to give you a recap of what we're doing and where we sit in the world. So the Epoch of Reionisation project is really looking at the first billion years of the universe, but really we're looking at about 500 million years to 1 billion years after the Big Bang. This is a time after the first generations of stars have formed and died, and it's really the ultraviolet light from these very early galaxies that is now going to be reionizing the neutral hydrogen gas that exists in the universe at that time. And so primarily the signal that we're looking for is the difference between the ionized regions where we expect no H1 signal and the partially neutral regions where we expect to have some fluctuations in the H1 signal. So it's primarily this ionized, non-ionized distinction that we're looking at when we're looking at this spatial distribution of fluctuations in the temperature of that gas in the early universe. So there are 3 primary experiments that are looking at this Epoch of Reionisation signal. There's LOFAR, which is based in the Netherlands. There's HERA, which is a very different type of telescope based in South Africa, quite close to the SKA MID site. And then there's the MWA here in Australia and the SKA that's now being built, which will be larger than all these experiments. To give you sort of an update on where these experiments are, none of us have detected the EOR in 21 centimetres yet. You would have heard about it if we had. HERA sort of has the best results to date, but anecdotally, they're having a lot of issues with their data that are sort of similar to the issues that we're seeing. And we also got a report recently from LOFAR as well. And LOFAR is a telescope very much like the MWA, and it's also finding the same challenges with its data set, the same challenges with its observatory site that we see with the MWA. And so really a lot of the work that we've done within ASTRO 3D is to try to improve our data, improve our models, improve our calibration and our methodology so that we can get closer to detecting this signal. But none of us are there yet. So in terms of redshift in the universe, the primary period that we're looking at is in this blue box here. It's about redshift 6 to 10, but the MWA does actually have access up to redshift 17, 18. That's really on the hairy edge of what we can do from a telescope point of view. Once you get to those redshifts, you're at a frequency below 100 megahertz. There you've got FM radio that we see over the horizon from Geraldton. It gets reflected off planes, it gets reflected off satellites. We have all sorts of RFI that we see. We also have the ionosphere, which is extremely active below 100 megahertz and wobbles our sky around. And in addition to that, the sky is just very, very, very hot at these low lower frequencies. And so it's really challenging to try and look into the cosmic dawn at those birth of the first stars. It's something that they want to do with the SKA. We've tried to do it with the MWA, but that's a very challenging experiment. So we've mostly worked in redshift 6 to 10. So this is a slide thanks to Nicole Barry, who's going to speak shortly. And this is sort of a highlight of where the field is across all of the different telescopes. The blue points that you can see here at the high redshift, but primarily at the low redshift, are the points that have been published by the MWA. The other colours are from the other telescopes. And what we're looking at here is the amount of power on a particular scale in the sky of that temperature fluctuation at a particular redshift. So there's lots of ways you can sort of slice and dice this field in terms of the parameter space that you're looking at. It's very hard to put it on one plot on a screen, but the take-home message here is lower redshifts are a bit easier than higher redshifts, and we're not really close to getting to where we think the signal is quite yet, but everyone is working very hard. Okay, so I've slightly updated this slide, which I've shown previously, about where the efforts have been within ASTRO 3D to try to undertake this experiment and get us closer to finding this primordial signal. So really, we're interested in the full end-to-end signal chain of our data. So we need to understand our sky. We need to understand our own galaxy and all the other radio galaxies that get in the way between us and that 21 centimeter signal at high redshift. The sky is 4 to 5 orders of magnitude brighter than the signal we're looking for. It's spectrally complex, it's spatially complex, and therefore it's problematic for us to try and disentangle this signal. So a lot of the ASTRO 3D work has been about building a better sky model, both those point sources, which are radio galaxies, AGN, star-forming galaxies in the sky, but also those extended galaxies in our own galaxy itself. And Nicole's going to talk a little bit about some of the challenges to do with that. We've had work on the ionosphere, on the telescope itself, how our instrument sees the sky, how we can do better with that. One of our PhD students, Ash, is about to talk about how the instrument can affect things, and a lot of work on the analysis, so the calibration of our data. Down the bottom there, we have our full end-to-end simulation, so we can understand what our signal is doing all the way through the signal chain, understand where our problems are. That's the Woden software that's led by Jack Line, who's a postdoc at Curtin. And Dev, now you'll see Dev. So this is the new part of this slide. So over the last year, Dev's really helped us develop a Nextflow pipeline, which is allowing us to look through our data and understand the quality of that data much more effectively than we've ever been able to do before. So if you could get a software architect, a software pipeline person on your team, then do it, because they make a massive difference to your productivity. So like I said before, what we'd like to be able to do is look at the sky at a particular frequency, because that's a particular look back time in the universe. We'd like to be able to map the temperature of that gas as we see it with our radio telescope, and we can produce these beautiful images of the sky as a function of redshift. We don't have the sensitivity to do that, so instead we use a power spectrum measurement. And again, this is one of Jack's slides. And effectively what we're doing is we're taking a cube of the universe on the left-hand side here of our temperature fluctuations. We're doing a 3-dimensional Fourier transform, and we're squaring. We're doing a little bit of averaging so that we're just looking at 2 dimensions instead of 3, but effectively we're looking at the amount of power that we have on a particular scale on the sky, and that's the metric of interest for us, because that tells us a lot about what's happened in the early universe, but it also collects a lot of information together so we can actually get at this weak signal. So this is a slide that I have shown before, and that's because there hasn't been any updated outputs from the MWA in terms of power spectrum lower limits. And that's because, as I said, all the work we've been doing here in ASTRO 3D has been trying to improve all the work leading up to that so that we can produce something that really is world leading and gets us closer to the signal that we're interested in. And that's what I'm going to talk about now. And hopefully we're going to have a publication later this year based on the work that we've been doing. So one of the large projects that we've had within ASTRO 3D for the full 7 years is to try and improve the calibration of our data, which is a really big deal when you work with a low frequency radio telescope. So this project's led by Chris Jordan at Curtin with a lot of support from Dev. And this is Hyperdrive. This is now software that's going to be open access. It can calibrate any MWA data, but it's particularly suited to EOR data. This is nearly ready for public release. It's very simple to use. It's well documented. It interfaces with a lot of other programs. It's interoperable, and it uses and allows you to use a lot of different data formats. And radio astronomers love their own little pet data format, and it's usually a real problem to work between those data formats. So that's almost complete, and that's a major output from ASTRO 3D for this project. One of the second pieces of work that has been a large part of the ASTRO 3D program is LOBES, the Long Baseline Epoch of Reionisation survey. This is a high resolution survey of the MWA fields so that we can have an improved sky model. This is led by Christine Lynch. This field is 60 degrees across. No, hang on a minute, what have I got? 4, 5 hours? Yeah, so like 75 degrees across in the sky there. There's 80,000 sources that are in this catalogue. And this is only the first half of it, and we'll be completing the second half of it very soon. This is the deepest, most high resolution, low frequency catalogue we have of the sky in these fields. And these are the fields that are going to be used by the SKA as well, because they're the best for our science because they're away from the galaxy. So one of the other pieces of work that the NextFlow pipeline has really enabled is the work to look at the quality of our data on a really large scale. So this has been led by Redeemer, who's also in the audience, and she has developed of order 20 quality assurance metrics on our data that go all the way from the raw data to the quality of the calibration solutions to what our power spectra look like on an observation by observation basis. And each of our observations is 2 minutes long. And what you can see here is just a snapshot of some movies of different observations going through. We're looking at the quality of calibration solutions. You can see that some of our tiles are very poorly behaved, so we don't want to have those in our data. And on the bottom left are some of the other metrics we have. And we're being able to collate all of this data together so that we can go through our full, about, I don't know, it's how many hours? We probably have about 3,000 hours of observations now. Go for those 3,000 hours of observations and really understand the quality of our data all the way through. Dev has we started a Google Doc to try and capture this, and Dev has very cleverly connected that Google Doc API directly into the NextFlow pipeline. And so all of these metrics get pulled out automatically and collected together into something nice like this. It's beautifully color-coded, so that we can actually look at the well-behaved observations that are in green and the naughty observations that are in orange and red that we don't want to deal with. And this is making our work much more effective and much and moving us much more quickly towards being able to produce our next result. So I'm going to show 2 movies now. Dev put these together. These are 30 hours of data in 30 seconds. So this is a field 30 degrees across. And these are all of the observations that have passed. The one on the left isn't actually running, but these are all the observations that have passed through the QA metrics. So I think it's about 1,600 observations. On the left is the sky as we see it after it's been calibrated. And on the right-hand side is the same sky, but with those point sources pulled out. How much longer do I have? 1 minute? Great, thank you. All of those sources peeled out. And so that's the data set we want to look at. But we have a large amount of data that we're working through. All right, so just in the last minute, I'm just going to describe one cross-project piece of work that we've been doing within ASTRO 3D. This has been led by 2 PhD students across 2 nodes and 2 projects. So Jaden Cook, principally, who's a final year PhD student at Curtin. He's not here because he's traveling at the moment. And Balu Sridhar is also a final year PhD student at Melbourne. Balu is in the room. And what they've done is they've taken the Genesis boxes, gravity only, in deference to Adam. They've then used Meraxi's code, which has been augmented to be able to produce a 21 centimeter signal, which is on top of those Genesis boxes. And then Jaden has put them through a little bit like SimSpin, but in the radio, Jaden's put them through a model of how the MWA would see those data. And he's actually then looking at those data outputs and understanding what our telescope would actually see with different models of the early universe. And on the bottom left here, you can see different astrophysics that have gone into the different models, so we can look at the discriminating power between these different models. So this is really where those Genesis boxes have been able to connect all the way through to what we would expect to see with our telescope data. And in this last year of ASTRO 3D, we'll be trying to put that together a little bit more. So I will just move forward. to lead this up, and these are the work plan milestones for MWA-EOR within ASTRO 3D as we define them at the start. You can see mostly they've been achieved. There's a few final ones that we're wrapping up, but really those big pieces of work that we wanted to do within ASTRO 3D have been achieved. And the bottom line one here, which is the unwritten one, is to produce a really good result for ASTRO 3D, which we're hoping to do with this latest big data run to get us as close as possible to detecting that early universe signal. Thank you.